Hi guys, hope all of us are doing great. My name is Ernest, and this is Ernest's Sciences and Mathematics TV channel. Today we're going to look at the concept of cylindrical capacitors. In our other videos that we have tackled on the similar concept, we have looked at parallel plates capacitors, and we're going to try to see what is the difference between that specific configuration and the cylindrical one that we're going to do today. But of course, as I said earlier, we're going to use the concept of a Gauss law. As we said, that this basically deals with the concept of symmetrical services and aspects which deal with the concept of charges and electrical field. A capacitor is one of the devices that we said which finds wide application in electronics. And one of the aspects of the capacitor is that it, of course, entails or exploits these specific aspects of course of geometry, electric field, and other aspects that we're going to see. Now I'm going to have a specific illustration on the board, and of course this is going to be, of course, a geometrical representation of a cylindrical capacitor that we're going to use. So suppose we have a cylindrical solid rod that is, of course, going to be able to hope my illustration is going to be okay. So if we have a cylindrical rod that is given as such, and this rod we are going to assume that it has got a radius of A at this specific point, and this rod is going to be surrounded by a shell, a coaxial shell that is going to be, of course, surrounding this one at this specific point. So we can just be able to assume that this is in between there. So if this shell has got a radius of let's say B, then therefore we can be able to find, and perhaps let's just give it a length from this specific point up to this one. The length from this point up to the last one, we can be able to illustrate it using L. Then therefore, if you consider this one to be a capacitor, then therefore we are going to give this specific central point to have a charge of positive. So we're going to issue this one with a positive charge, and this one with a negative charge, and the inner surface illustrated as such. So we can consider this configuration to be a cylindrical capacitor, and therefore we can be able to find its capacitancy by trying to exploit some of the, of course, geometrical features that we know from basic geometry. So in this particular case, we had talked about the Gaussian surface being an imaginary one, and therefore we are going to, as I said, consider the Gaussian law in trying to find which is the Gaussian surface that we're going to consider. Now we're going to have a particular, of course, a relationship that is going to be given for this Gaussian surface, whereby we're going to consider our Gaussian surface to be coaxial to these cylinders as well. So it's going to be an area that is going to be bound by this specific radius. So this radius, we're going to give it at this specific point, and it's going to be illustrated by R. So therefore, this specific R is going to lie between A and B. So implying that A is greater than, R is greater than A, but it's going to be smaller than B. That is going to be form our imaginary surface that I've demarcated for the Gaussian surface. And this coaxial cylinder of our imaginary surface is going to have a length of L, small lowercase l, which is smaller than the length L. So therefore, we're going to consider these specific conditions for our Gaussian surface. And this, of course, is due to the fact that the electric field in this particular case has to be confined within that region that we have given for this specific comparison. For the reason that whenever R is greater than A, then therefore we're going to see that the enclosed charge, which is Q enclosed, is going to be 0. So that is going to form a difficult for us in trying to compute that specific charge, since the net charge in that specific conductor has to be restricted, of course, within the surface. So therefore, we're going to consider a case whereby as well R is greater than B. And under this surface, of course, we're going to see that the charge enclosed is going to be the difference between, I'm going to show this specific, what this specific lambda stands for. And therefore, this is also going to be the net of 0. Since we had said that for Gaussian surfaces, the opposite charges are going to reside on the different sides of the conductor. And I've given the concept that the net charge of a charged capacitor is going to be 0 for both a charged and uncharged status. So in this particular case, that is why we have restricted our Gaussian service within these confines of R, which is greater than A, but smaller than B. So in considering the figure that I've given above, we're going to assume that the inner part is positively charged and the outer one is negatively charged, and try to calculate what we term as the electric field on that particular service. And of course, this is going to be done using the integral function that we had given for Gaussian law. So we're going to give an integral of a closed service for this specific area, whereby we're going to see that it's an electric field, and the dA, that's a vector service for that Gaussian service. And then this is going to give us what we call EA for that specific integral. Now, if you try to look at this, of course, the A is going to represent the area, the surface area, which we know for a cylinder, it's going to be, this shell, it's going to be 2 pi r L. And this L, I'm going to use this one for the Gaussian service, but I've indicated for this specific condition. So therefore, in doing a substitution for this, we're going to have EA represented as EA is equivalent to E 2 pi RL given as such. So that's going to be our Gaussian service. And therefore, if we try to look at that specific condition, I had said that, now in this case, we had said that to find the electric field everywhere for our Gaussian service, then we're going to use this specific relationship that we had stated that the EA, which is the right part of the equation, can be represented in this particular case by the use of what we refer to as the Q enclosed over the epsilon naught. So in this case, if you try to do a comparison between this second part of this, we can do an equation whereby we are going to have this one represented as Q enclosed all over epsilon naught is equivalent to E 2 pi R L. And this, let's say this is our equation 1, and this is our equation 2, and this is our equation 3. So from there, therefore, I hope I think I'm just going to do away with this. We create a space here. So from this particular last equation, then therefore we are going to say that for us to find what we refer to as the charge per unit length, we are going to use this notation for lambda, which is going to be represented as Q over L. So therefore, in us to try and find out what is the charge that is enclosed in this specific case, and therefore we're going to make Q the subject of the formula, implying that we're going to have Q represented as lambda L. So therefore, we're going to do a substitution in this specific case, whereby we are going to have lambda L in place of a Q over epsilon naught is equivalent to E 2 pi R L. So if we try to see this specific equation, we're having L and L represented thus, we can just cancel that for simplification. So in this case, we can make E, which is going to be represented as a subject of the formula. In this specific case, I'm going to do away with this so that we can have a space. So we're going to make E the subject, and therefore this one implies that E can be represented as lambda over 2 pi epsilon naught R, given as such. So that is how we're going to represent an electric field of that specific cylindrical capacitor. But if we try to see, we had said that we are going to find the capacitance by trying to compare the electric charge and the potential difference. And therefore, we're going to look at the condition whereby we're going to have an integral of that specific difference, that is a bit delta V, and we can achieve that one by, we had said that capacitance can be given as Q over the magnitude of the potential difference. Therefore, it will be incumbent for us to try and find out how we can find the potential difference in this specific configuration. Therefore, that is going to be delta V is equivalent to V at B minus V at A from this specific configuration. And I would say that this is equivalent to the negative value. Since we're going to see that this one is going to be a negative value and a positive, therefore we're going to have this one being a negative integral from A to B, from B to A of this specific electric field within this radius of R, which is going to be given. This is R and not V, ER dr, and that is going to give us an integral for finding delta V. So from this specific case, we have already calculated the ER in this specific point. So therefore, we're going to do a substitution and write this one as a negative B A over lambda 2 pi epsilon naught R over dr. And that, of course, is going to give us that specific integral. So this, of course, we're going to consider that from the laws of our integration, we're going to take the constant out, and this is going to, of course, give us a derivation that is going to be given as the integral of negative 2 pi epsilon naught. That one is a constant from B to A, and then we are going to have dr over R given over that specific range. So this is going to give us a result of lambda 2 pi epsilon naught, and this, for this section of R, we're going to consider from B to A. Therefore, it's going to be the difference. So for this reciprocal of 1 over R, then we're going to have the natural log of B over A from the laws of integration. That is going to simplify into that. And this is going to give us what we refer to as delta V. So of essence for us to draw and note from this specific case, of course, is that we were trying to find the concept of a Q, and we'll say that Q can be represented as lambda L, and then V can be represented from this specific derivation as lambda over 2 pi epsilon naught, and then the natural log of P over A. So these specific two quantities are the ones that we're going to find a ratio that is going to assist us to represent the capacitance for this specific configuration. So therefore, we're going to have the ratio between the two, whereby we're going to have the capacitance being represented as Q, which is lambda L all over, and then we have this specific difference in potential difference. So this is going to be lambda over 2 pi epsilon naught, and then we have the natural log of B over A. So we can redo a rearrangement for this specific fraction that is under another fraction, so that we can simplify that specific representation. So we have C, which is going to represent, so for the values of lambda, that's going to cancel out, and this is going to give us a 2 pi epsilon L, and then we're going to have that one all over the natural log of B over A, given as such. So if you try to see this simplified form of an equation for representation of capacitance, therefore it's going to consist of these specific constants, and these are the dimension for the radius of this cylindrical part for the inner cylindrical rod, and then for the outer shell that is, of course, a coaxial shell that is, of course, surrounding this specific rod. And then, therefore, we can have a conclusion that the capacitance of a cylindrical capacitor is going to depend on the geometrical factors, which is basically L, A, and B, which are geometrical factors of this specific configuration. From our first case, we are saying that for the, of course, parallel plates, it also depended on the configuration of those specific parallel plates, and therefore we are given that formula. If we can remind ourselves from the parallel plate, we had said that capacitance is given as epsilon naught A over D, where A was the area of those parallel plates, and then we have this D as the distance of separation between them. So from our first case and the second one, we can be able to conclude that capacitance basically depends on the geometrical factors of those specific capacitors. And lastly, we're going to see the case of a spherical capacitor and try to see whether that is going to also play or rather display the similar feature. So catch us in our next videos. We're going to look at the last part and of course a third part of the cylindrical, the configuration of capacitors, which is a spherical capacitor. Kindly check on our comment section for, or rather our description boxes for various links of similar videos, which are going to assist us, of course, comprehend these specific concepts in deeper details. So that is it for now. Bye, guys. God bless you.